Hello everyone. In this module we're going to introduce hypothesis testing, and we're going to get into the details of hypothesis testing and different types of them. We're going to talk about central limit theorem and the two types of errors that can happen in any hypothesis testing, because no hypothesis testing is perfect. We're going to learn about how to compute or approximate probabilities associated with the sample mean. We're going to start with that. Learn how to formulate statistical hypothesis tests, estimate population means, and conduct two-sided hypothesis tests. And then we're also going to talk about one-sided hypothesis tests later. When you think about hypothesis testing, is one of the methods in a bigger area of statistical inference. And statistical inference is a set of methods used to draw conclusions about a population or one or more random variables. So when you want to draw conclusions about a population, one of the methods is to use hypothesis testing. The specific topics involved is point estimation. Essentially, when you're estimating a single point, like single point. So basically X bar is a point estimation, and it approximates the true population mean of mu. And then we have interval estimation. Interval estimation is not a single point estimation, but you're essentially providing an interval. You're saying that average, the true population mean, is in a certain range. That's an interval estimation as opposed to point estimation. And then hypothesis testing is a method to basically evaluate the robustness of your claim about any population. Robustness of your claim. So you might have a claim about a population saying that average salary of nurses in Southern California is $65,000. That's a claim. And with hypothesis testing, you would be able to evaluate that and see how correct is that. So to get started, we have to say that a statistic is a random variable. What is a statistic? Basically, is a function of the observations in a random sample. So if you take a random sample of, let's say, the same example, salaries of nurses, of let's say 50 nurses randomly selected, an average of those salaries is a statistic because it's a function of those 50 observations. And what we're saying here is that a statistic is also random. It's a random variable. Let's take this example. Let's let xi be a random variable representing the cholesterol level of an adult. Okay, you plan to measure the average cholesterol level of 10 adults. Basically, you're looking at x1 through x10, and each of them are random variables because before you observe them, and they're associated with cholesterol level of 10 adults, and you don't know them, so they're random variables. And then x bar be a random variable representing the average cholesterol level of 10 adults. Basically, x bar is the average of those 10 cholesterol levels. So when you think about it, this x bar itself also is random, because if you take a sample of 10 cholesterol levels and you take the average, you might get an average, and then you take another sample of 10 adults, you probably get another average. So x bar itself also is a random variable. So when you have a random variable, let's say x bar, which is sample average, it should have a distribution. It should have a probability distribution. That is called sampling distribution. So when, because a statistic is a random variable, it has a probability distribution. It's called the sampling distribution. In fact, the probability distribution of x bar that we just looked at is called the sampling distribution of the mean. Okay? And this sampling distribution depends on your sample size. And you will see how. Sampling distribution depends on the sample size. So how does this sampling distribution look like? When the underlying population is normally distributed, let's say those cholesterol levels that your individual cholesterol level is normally distributed, then the sampling distribution of the mean or any statistic will be normal. Because that's actually can be proved fairly easily. If xi values, x1 through x10 for the cholesterol level example, are normally distributed, then x bar, which is the average of those xi's, is a linear combination of normal random variables, so it will be normal. That is very straightforward. If your underlying distribution is normal, any statistic coming out of that is going to have the sampling distribution of normal. But the more fascinating part of the story is that even if the underlying population is not normal, the sampling distribution will be normal anyway if your sample size is sufficiently large. So if you pick a really sample size of big enough sample, the distribution of the mean, the sampling distribution of the mean, will be normal anyway if your sample size is large enough. And this is because of central limit theorem, and we'll get into central limit theorem here in a second, but that is a very fundamental fact about hypothesis testing, which is the underlying foundation of this. So let's get actually a little bit more mathematical. If x1 through xn is a random sample of size n, taken from a population with mean of mu and variance of sigma squared, and if x bar is the sample mean, x bar will have a normal distribution with the mean of mu and variance of sigma squared over n as n gets larger, goes to infinity. So this is a very important slide here. Basically what it says is if x, your initial observations, has an unknown distribution, let's just say unknown distribution with some average and some variance, x bar, okay, x bar's sample averages coming out of this distribution will be having a normal distribution with average of mu and variance of sigma squared over n. Okay? And this x bar is the sample average of size n, right? So this is essentially what we're saying, that your sample average is going to have a normal distribution. And if x bar is normal, the z value associated with that, so basically the associated standard normal random variable, is going to have this formula. And this is x bar here. So z will be equal to z x bar minus mu, and this is this mu, over sigma over square root of n. And that is based on this, because if this is the variance, the standard deviation would be square root of sigma squared over n, which is sigma over square root of n, right? And this is true if your n is sufficiently large. This is the underlying assumption. And a rule of thumb for sufficiently large n is n of greater than 30. So if your sample size is greater than 30, then your x bar is going to have a normal distribution. Let's put this in a more graphical, maybe summarize everything in a more graphical way. So let's say that you have a population of something, a random variable. So this is your population. And this population has a mu, basically a true population mean, and a variance, right? And you're starting to take samples out of this population. You take your first sample, right, x1, x2, all the way to xn. This is your first sample coming out of this population. Let's say that population is all the patients available to you, and this sample is n of those patients that you're basically calculating or taking their cholesterol level. And then for this sample, you would have a sample average and you would have a variance. We call that variance S squared. And then you take another sample, right? Another sample, x1, x2, another 10 or n patients cholesterol level. And then you take the sample of that, take the average of that sample, take the variance of that sample, and you keep doing that, right? You will have another x bar, another variance. What I'm saying here is that these x bars, let's call this x bar 1, x bar 2, x bar 3, these x bar values will have a normal distribution. That's what I'm saying here. So and they have a sampling distribution. This is called the sampling distribution of the mean. The sampling distribution of the mean, which is this mu, will still be approximately normal with mean of mu and variance of sigma squared over n. Basically, x bar values follows a normal distribution with an average of or mean of mu and sigma squared over n. And keep that in mind that this mu is the same as this mu, and this sigma squared, and this n is your sample size. This is basically wraps up the central limit theorem and the sampling distribution of the mean that we needed to discuss in this video.